Welcome. Thank you for attending the webinar. My name is Joseph Edzorek. I'm a product manager on the AWS services team at Amazon. Today in this webinar, we're going to talk about purpose-built databases and choosing the right tool for each job. Agenda for today is we're going to talk a little bit about, what do you mean by purpose-built? We're going to talk about working backwards from the problem and choosing the right tool. We're going to go through what we see as the common data models and use cases that we see a lot of developers using today on AWS. We'll go into a quick demo, and we'll finish with some customer examples and additional resources to learn more. So a few weeks ago, Werner Vogel, the CTO of Amazon, published a blog entitled "A One-Size-Fits-All Database Doesn't Fit Anymore." And I think, what Werner's really trying to say in this blog is that the way that databases are used today have really evolved. And I think, he goes in kind of better than I can say it, is, a common question we get from database developers is, why do you offer so many different options? And Werner answers this succinctly is that, customers today or developers today want to be able to write or build well-architected applications, and to do that, they use a multitude of databases. And it's true, we do offer a lot of different database services on AWS. RDS, we have Postgres and MySQL and MariaDB, and Oracle SQL Server. We also have Aurora for MySQL and Aurora for PostgreSQL. And the non-relational side, we have DynamoDB, Elasticache or Redis, Elasticache or Memcache, Neptune. There's a number of different choices. But what we see, especially in technology with so many choices, if things don't have a value for databases, if databases don't have value, then customers don't use it. But we see that customers are using these types of models over and over again. So how did we get to this point today? Well, if we kind of take a couple steps back and we look at how databases evolved, the first 2 decades, we really had, 3 stalwarts of databases in, Oracle and DB2 and SQL Server, and all those databases are relational, and they pretty much were the dominant way that people stored data in those decades. If we move forward to, the 1990s, we saw the appearance of, the first releases of MySQL and Postgres, again, relational databases. However, if you look in the last year, we see a significant rise in a number of varieties of data models that have popped up that people are starting to use. And we look at this and say, for the past decade, it really wasn't the purpose or the function that was leading to the choice of the data model. It was actually the other way around. There was only one way to store data, and that was driving the choice of data. Now developers have many, many more choices. So why is this? Well, we really look at the applications that were being built in the 70s, 80s, and 90s are fundamentally different than the applications that are being built today. We think about, if you look at your phone, you look at the applications that are on your phone and Lyft and Airbnb and social media, those applications have, daily millions of users, data volumes in terabytes and petabytes, easily accessible globally. Whenever you go on vacation, you go out of the country, you expect those same applications to work wherever your final destination is. Performance has been, reestablished now in microseconds and milliseconds with the expectation that these experiences are going to be fast. Think of Snapchat during New Year's Eve. That's request rates in millions, tens of millions of requests per second. These are just not workloads we saw 2 decades ago. Everything is expected to be on mobile IoT devices and scale every which way you can think of. And from a developer's perspective, you want access to instant APIs. You don't want to procure a license and have it show up 3 months later and wait to somebody to install it for you. If you have an idea, you want to be able to implement that today. You want to start using that API today, and you want it as a pay-as-you-go model. You don't want to have to be bought into something for lengthy licensing schedules. So just fundamentally, the way that we build and think about applications has changed, and so are the data models. So when we talk to customers about the databases that we have at AWS, the one word that we really use to frame this discussion is purpose, right? Things that have a purpose exist for a reason. And one analogy we really like to use is trucks. I think this is a pretty tangible example for many people. Let's say we have, the use case or the desire is to move a mattress across town, or we want to haul a boat. We're probably going to pick that pickup truck in the bottom left. That's its purpose. It's really good for that. We can throw some people in there, maybe even haul some mulch from Home Depot on the weekend. But if we need to move packages across country from East Coast and West Coast, we probably don't want to use that pickup truck because depending on the size of our load, we're going to have to take multiple trips and it's not going to be efficient. For that, we probably want to use an 18-wheeler. On a similar note, if we're going to deliver packages in downtown Seattle, we want to use something that's purpose-built for handling the tight corners of downtown Seattle streets. We want to have that door optimized to be open because every second of that driver's day is material as far as how productive they can be. And it's really good at being able to navigate, very tight streets and corners. Now, if we look at the three examples that we just provided, and we say, hey, the next use case is we want to redo the SeaTac airport, and we need to haul, metric tons of dirt. We're not going to choose a pickup or a semi or a delivery truck. We want to use an earth mover. The reason it's purpose-built for that specific use case, sure, we could modify either one of those other three trucks to do that job, but it's going to be more expensive, it's going to take more time, and we're not going to be able to accomplish our goal with any reasonable amount of time. Right? And if trucks doesn't do it for you, there's a lot of other things that have purpose. Golf clubs have a purpose. You don't use your putter for every stroke on the golf course. Tools, everybody knows, the hammer and the screwdriver and the wrench stories. Knives have a purpose. You're probably not going to carve a turkey on Thanksgiving with the same knife you're going to cut vegetables with on the weekend. You're certainly not going to make spaghetti in a fry pan. Each of these is examples of things that have purpose. So when we start to talk to customers about what database to choose in which situation, we really frame that conversation to start working backwards from the problem that they're trying to solve. What is the shape of the data? What are the axis patterns? And then working backwards from that particular problem or use case, then choose the right tool for each job. Right? And we see customers doing this already today. I mean, imagine, when you've booked a property with Airbnb and you go to their website, there's a whole bunch of different experiences there, whether it be search history or even the session state. Hey, what am I doing in this current browsing session? That data has to be persisted and stuck with you. And even the simple transaction of purchasing or renting out a particular spot for a weekend, those are all different types of data models, and we see Airbnb is a great example of using multiple purpose-built databases for different experiences on their site. Expedia is another example. Think about the dynamic pricing when you go to, you look at a new rental. You have your same type of transactional data, operational data, what they're using Amazon Aurora for, and there's a really great talk at reInvent last year on this topic. Also using analytics for understanding, hey, how are customers using our website? What should we expect next year? How should we make this better? Running analytics in Amazon Redshift. So we have multiple different purposes using multiple different data stores. So we see 6 common data stores that developers are using, and we'll go through each one of these in a little bit more detail. So we'll go through them a little bit quickly now. So we have relational, which has been around. We talked about that for decades. We see key value stores, document databases, in-memory stores, graph databases, and search stores as well. So we see 6 fundamental data models and use cases. Now, for relational databases, the problem that relational tries to solve really goes back to some of the most fundamental exchanges of money that existed, that predate a lot of certainly all of us, but a lot of modern technology. And as simple as saying, hey, I want to debit money from one person's account or one person's holdings, and I want to credit another person. Now, this problem is still challenging, but relatively easy to solve when you have one person that has the book and the one person's making that debit and credit statement at a time. This problem becomes much more complicated when you have multiple people, concurrent users trying to make changes to account values at the same time. We don't want to double debit one credit or one account and then lose that money or subtract more money than what the person has. There's a lot of controls that go in place to make sure that these situations don't happen. And this is where relational databases really shine with the capabilities of ACID transactions. We see these a lot in financial applications, as we saw with Lyft and Airbnb. We also see them in EMR and CRM applications. In relational databases, if you kind of go back and how they were built, they were really optimized for on-disk storage. So that was the constrained resource back in the day. So we wanted to normalize the data and to reduce the footprint of the data to as small as elements as we could. And the way we did that was through normalization. You might be more familiar with primary key and foreign key relationships. So we only wrote the data once and we had a one-to-many relationship. What this is really good for is that the database is able to enforce the schema or enforce these referential integrities. So imagine we purchased an item online and we tried to delete a product from the database, but it had a primary foreign key relationship to the orders table. The database would prevent us from deleting that product because it would orphan an order and we would have no way to do attribution back to what product that order was created for. So the database enforces that relationship. We also see relational databases are purpose-built for having schema on write. And what does that mean? Well, it means when you write data to the database, you're writing to a fixed schema, and that can be very advantageous for cases where you want to control and have the database enforce that schema. We'll talk about the document databases in a little bit. Is a little bit different of a database style where it's schema on read, where the database doesn't necessarily enforce the schema, but the application does when you read the data. Just a little bit different style of working with data. Okay. Now, a question we get a lot is, hey, we saw on the slide, hey, there's all these new different types of databases. You go to Database Engine, there's 340 plus different databases being tracked. Is there still a place in the world and do relational databases still have value? I mean, the answer to that question is fairly simple, and the data speaks for itself. It's absolutely yes. What we see is, Amazon Aurora is still the fastest growing service in AWS history. And you look at the customers on this slide, it's not like it's going away. What we see is customers increasingly using relational databases, but additionally augmenting their customer experiences and their applications with different types of data types to provide different levels of experiences or different types of experiences for their customers. So it's not necessarily a replacement, but complementary. On a similar note, when we talk about relational databases, we also talk about columnar stores like Amazon Redshift. Now, what is typical in a relational database, let's say we created a school store, and imagine this was the most successful school store ever, where we sold pencils and erasers and staplers, and we got pretty good at this. It'd be very natural for us at the end of the quarter or at the end of the week to want to run some type of analytical queries for say, hey, we want to know, what is the quantity of items that we sold from a product table this day, week, or month. Now that problem is pretty easy to solve, and relational databases afford these types of queries. Where this becomes problematic is when we have very large sets of data, hundreds of gigs, maybe terabytes of data, but we also have customers running financial transactions on that same database, right? For that sum quantity query to complete, we have to read every single row in the database. So what columnar databases did is they came along and said, well, what if we kind of pivot that schema 90 degrees and we store the items that are in columns in a data structure? So we want to run these analytical queries over a single column. All that data is stored in the same data structure and actually becomes much more efficient, say, to run this select sum over the quantity column from this product table. We don't have to touch every row in the database. We just have to read the data from that particular data structure. And we see Amazon, Redshift is an example of a columnar database that provides these capabilities. It's just a little bit different way of storing and accessing tabular data. Well, unlike a relational database, key value stores are very self-descriptive. They have a key and a value, and that key is able to be highly partitioned across multiple different servers. And because the data, like relational databases, doesn't interact, keys and values don't have that referential integrity between the two different entities, you're able to scale horizontally to nearly boundless ends while still providing the same consistent throughput for those key value lookups. So we see a lot of customers using key value stores for real-time bidding, shopping carts, IoT tracking, where just that key value of data is sufficient to perform the operation the customer is looking for. So we go on, we start looking at other data models. One of the ones that has become particularly popular in the past decade is document databases. And one of the motivations for document databases was JSON became kind of the de facto standard for serializing data between clients and applications, or even changing data within the applications. But then when it came to persisting the JSON document into a database, there's this impedance mismatch. I had a nested document that, it was intuitive for me to understand, but now I had to shred that document and put it into some normalized form to match the schema of my database. And what really came about from that is you get databases like MongoDB and DynamoDB that provided a document as a fundamental entity of the database, not a row, but a document. And we see a lot of customers using document databases for content management. One big use case is even just indexing items that sit in S3 as a way to describe and query the metadata that talks about what is in an S3 bucket. Personalization, if you can imagine, patient records or user profiles, it becomes a very intuitive way to deal with that data. Right? So we look at how developers think about actually using documents, and it becomes actually a much more intuitive way, especially in the application tier. In your mind, you don't really think about or normalizing data across multiple different schemas and then being able to construct that back in your mind to be able to write the data. ORMs kind of popped up to try to help solve this problem, but they also caused a little bit of friction. It becomes much easier just to pass JSON, plummet through from the client to the app to the database and back again without having to do that translation. Now with in-memory data stores, so this is a little bit fundamentally different system, and the use cases we see here are for customers wanting to do very high throughput, very low latency scenarios such as leaderboards. And I think Twitch is a really great example. Very high concurrent users, but if when you've played a game or you've watched a child play a game, one of the most gratifying things to experience is after the game you get to see what the leaderboard is, or you get to see what your standing is in the game. Now, if you had to construct that leaderboard for every single user by reading all of that data off of disk, that would be a very slow query and you would not get that immediate gratification. So you see databases like Redis that provide ordered sets that make it very easy to have not only the data structures, but the in-memory capabilities of high throughput, low latency to make these experiences really fast. And we also see, like caching is another enormous use case for in-memory stores. Pretty much most of technology, runs on some form of caching, whether it's a website, caching images either locally on your browser or on the edge, on your phone, you cache a bunch of content and then you go read cache content on the server side. Caching is just a fundamental technology that really underpins a lot of the experiences we use today across many different types of applications. And the way that this happens, you kind of like, and I know you're sitting here saying, Joe, databases are much more technically complex than that. I hear you, completely understand. But this is just kind of just trying to show an example of how in-memory databases are fundamentally a little bit different than, say, a document store, key value store, or a relational database. So typical databases, we have some type of query processor, some type of memory or buffer pool, a storage engine, and then all that is persisted in disk, and this works all in perfect harmony. What we see with in-memory databases, if we remove that disk, then we get we don't have persistence, we have ephemeral data, but we also improve the throughput and latency significantly by just being able to read directly out of memory. We don't have to do those slower, typically 10 times slower random seeks to disk. We can just serve those particular requests straight from memory. And for many scenarios, that is sufficient and actually advantageous to deliver those types of experiences. Graph databases. So graph databases solve a different problem when we talk about how we want to query data. We talk about connections between data. And the real typical use cases here are, hey, recommendation engines. And you can see by my recommended books is that the variety of books I read are very limited and basically focus on product or business. Other use cases, we see a lot is recommendation engines, especially within social networking. You've gone to your LinkedIn account and, quite often, say, hey, here's some recommendations of people you might know because they are friends of friends or colleagues of people that you're already friends with. These are graph types of use cases, right? And graphs are fundamentally different in the sense is they talk about relations between entities. And some people say, well, isn't relational database, doesn't that have relations in it? In a relational database, the relations are about primary foreign keys to construct a row out of multiple normalized tables. When we talk about relationships within a graph database, and we'll do an example during the demo, is that we really want to know for that particular row, what is that row's relationship with something else? And we bring this into as a first-class citizen of describing these relationships between entities, and those relationships themselves can have different types of attributes, like, hey, this person has a skill, and that skill can be associated with a magnitude. We can use all that to query graphs much more efficiently and provide a lot more richer result sets. And the last last data type that we're going to talk about today is search. And search, the use cases we really see for this are product catalogs, right? When we go to, say, Amazon.com, and earlier in the weekend, we were at the lake and somebody had this very obnoxious unicorn floaty, and that was an item we must have, but we didn't quite know how to describe that. We come home, we type in Amazon, pool unicorn, and it gives us a list of highly relevant types of results that would relate to those words, those keywords that we put in. Now, to be able to fulfill those use cases, it's a fundamentally different data type, and we'll talk about in a second. The second use case I really like here is, like help and FAQs. Every time I have to leave the country, I have to go to my credit card company and tell them that, hey, I'm going to be out of the country, in these destinations for these dates. But I can never remember where on the website I need to click to do that. So I always go up into help and I type, international travel. And you can always tell on how well that particular experience is implemented. And you can almost tell what kind of data store they're using behind the covers by how relevant the search results come back and how curated that list is. So to be able to do these types of experience, this is different than a key value store, it's different than a graph database, it's different than a relational database. Search data stores work on documents, and they use something, different people call it different words, but they call it a stop list, which takes out articles and adverbs and some words that you're really not going to key on, and then stores those keywords in what is called an inverted index. So when you search for these keywords, the search and retrieval for the documents that contain these particular keywords are much, much faster. Now, could you create a search experience out of a relational database? Certainly, but when you get to a certain limit or a certain type of functionality, that's a scenario in which you can get into trouble by overburdening a database beyond what its intended purpose was. So there you have it. So those are the 6 data models we're seeing customers use today. So now to make it a little bit more real, let's go into a demo and show a little bit of how these data models can be used together to deliver experience. A common question we get is, hey, can we choose one? Do we have to choose one data model for our entire application, or how do we use multiple databases together? So what we're going to show is in this particular demo, we're going to use DynamoDB, And then we're going to use DynamoDB streams with Lambda to be able to take an item that I'm going to insert into our products table and then write that data to Amazon Neptune and Amazon Elasticsearch Service so that we can use that same data in multiple places within our application. So I've created an experience here. If you can imagine, we're going to sell calculators as an e-commerce website. You can imagine, like, you know, one of the first experiences if we're going to build this website is our product catalog, right? We have our calculators, and that's kind of the, you know, that's the item we want our customers to buy. But we also want to go up here, and we also want customers to be able to search for calculators, you know, based on some type of description. And those are two different types of experiences that typically use different data models. You know, for the product catalog, I'm going to use DynamoDB, but I also want to use Elasticsearch for this search experience. So how do we do that? Well, so let me go to the DynamoDB console, and I'm going to create a new table, and we'll call this live demo table. And for the partition key, because we're doing products, we'll call it product ID. And we're going to create that table. Right? So as this table is being created, we want to next, as we saw in the architecture for this particular experience, we want to enable streams. And what streams is a feature that every time we either write to or modify or delete an entry in our DynamoDB table, it makes a record of that action and writes it to a queue or a stream that enables us to read that queue and be able to process that data with, say, a Lambda function so we can take an action on it. So in our case, every time we insert or modify an entry in our product table, we want a function in Lambda then to write that to our Elasticsearch index, so our product search capabilities are kept up to date. So let's go ahead and enable streams. And the next thing we're going to do here is we're going to add a trigger. And the trigger is that Lambda function that's going to process that record every time it is written to the streams. So we're going to use one that I've already created. And we're going to put the batch size down to 1. So every time an individual item is written, that'll get reflected in our Elasticsearch index. And we'll create that. So let's go take a quick look at what this code actually looks like. So we're in the Lambda console, and I've already written this ahead of time. But in this code, what is essentially happening, there's a lot of cruft here, but if the event is either an insert or a modify, what we want to do then is be able to say, hey, let's take that record and then let's write this to our Elasticsearch index. And that way, asynchronously, every time that we go through, we get to keep everything up to date, and it becomes a really slick way of combining multiple purpose-built databases together. So let's go ahead and let's write now a row into the table and see if that gets reflected into our Elasticsearch index. All right, so let me open up my script, and we're just going to insert an item. We'll call our calculator the number muncher 22. We'll make it fairly cheap, and with warehouse, we'll put that in Ames, Iowa. All right. So now we're going to insert this record into our DynamoDB table. We're going to go back. So let's go back. I've already created a product table ahead of time that's already associated with the demo. So let's look in that products table. And we can see our trigger that we processed on this table, that one that we wrote to, we processed that result okay. So we can go to our items. We can look down here now for the number muncher. There it is, $19.99. What a heck of a deal for a calculator. And the warehouse is in Ames, Iowa. So now we want to go back to our store, and we want to be able to make sure that our new product is there. right? So we have the number muncher there, but if we talked about this in social media and someone didn't quite know about it and they wanted to search, they thought they heard number, sure enough, they can use that search experience. They don't have to say number muncher 22, just number was sufficient to bring that up. So there's an example of using two purpose-built databases together. Now, another experience that we commonly see, especially in this domain, that customers want to use perhaps another database for is this experience down here. Hey, great, I bought the number muncher 22, but what are the other items that my friends have frequently bought together? Did they also, have to buy a different calculator for some advanced calculus class or a notebook or a case? Now, to deliver that experience, one of the databases we see that are a lot of value here is a graph database, because this is really about talking about a graph of relationships. So now ahead of time, I've constructed a graph of what my world might have looked like back in high school. And the blue dots here, these are called vertexes. And you can think of vertexes as nouns, right? The blue ones are people, the dark blue ones are people. So you can see Joe and Ted, and Joe knows Jess. And we can quantify these relationships, right? So I've ranked my friends, 0.9 means they were a better friend, and 0.4 means they weren't as great a friend. And we can also have relationships where, Dan also bought a math or a biology math reference, and Ron bought or attended a class which was biology, which I also attended. Ted also attended math. And we can start to ask questions of this social graph for saying, hey, of the friends that I have ranked in order of the ones that I like the most to the least, what are the other items that they purchased? And doing this with the graph database, it becomes a much more intuitive query language, right? So let me show you how this works. All right, so I wrote a query ahead of time, and let me walk you through what this query is actually saying. So the V's are vertexes, and we're going to use the Gremlin query language. So the V's are vertexes, and I'm V1, that's Joe. And I want to go out from that vertex. So imagine all those lines or those edges connecting to the other vertexes in my graph. And I want to know for the ones that I know, which typically will point to people, I want to order them by a weight of increasing importance, right? And then from there, I want to take those particular vertexes. I want to see what items those people have bought. And for those items that people have bought, what are the names? And we'll dedupe the result set, and we should see, just like we had in our graph, there is only 4 items that people could have bought: a math reference, AV cords, charger, and paper. Now, to make this useful within my application, I don't want the actual friendly names. I want to have the GUID so that I can match that up with the products in my within my product catalog, and I can change the value, which is an attribute of one of the vertexes, from name to models, and I can get that GUID, and now I can go back and deliver this experience back in my website. Right, so now I can come back and I can feed that data back into my website. So there's one example of using multiple different purpose-built databases to power a single experience. And next time you go to a website or your favorite application, and I always like to do this, but maybe I'm just a data nerd, is really look at those experiences and think about how those are constructed behind the scenes. What type of data model or data type would you use if you were designing that application to provide your customers the best experience for those particular use cases? So when we talk to customers, that have already been doing this and, have been proponents of, picking the right tool for the job, the feedback that they give us is, when you use the right tool for the job, you get better performance. Could I create a graph database out of a key value store? Absolutely. But what I'm going to be doing is I'm going to be doing a lot of those queries in the application tier. I'm going to be doing a lot of things that are unnatural for that data store. And it's going to cost me more, eventually it's just going to cost me more time to do all that processing, because I'm not pushing that down to something that is highly optimized for those query patterns. Similarly, we see, especially can you create a Can you create a data warehouse out of, a graph database? Sure, I'm not sure why you'd want to, but you wouldn't have the functionality that is there. Document databases have all the bells and whistles to be able to handle indexing and manipulating and querying documents. Same thing for relational data stores with strong referential integrity and ACID transactions. Duplicating that type of functionality in data stores that don't have them just takes time away from adding value to customers, and you start reinventing the wheel on data stores that weren't built for that purpose. People come back to us and tell us that they're easier to debug, especially when you don't have, when you think about a monolithic database and imagine an entire application running on one database instance, and you have multiple different concurrent types of queries coming in from multiple different parts of the application and in different teams within an organization, those become very difficult to debug of who's taking resources and how do we separate out and who do we figure out who the offenders are. When customers or when developers are able to tease those applications apart into microservices or different technology stacks, we find that much easier for them to be able to debug, and also gives teams independence to choose what is the best tool for the job or which one they prefer to use for their use cases. So we see a number of different customer examples, and there's a really great talk, the last 10 minutes, specifically talking about purpose-built databases by Team Internet at reInvent last year. And this predates, the creating of my slide deck, but I think, or the slide deck, but I think what you really see here is, they started off with this monolithic application. What they ended up doing was teasing apart their application, their tracking API, the real-time bidding engine, and their stats APIs into 3 different databases: a key value store relational database and a Columnar data warehouse, to provide their customers with the right experience that they needed. Another really great resource and a really great place to find how other companies, perhaps similar to yourself, are architecting applications is through the This Is My Architecture video series. And these are really nice, 5 to 7 minute videos that provide an overview of how particular experiences in different services that you probably already use today are constructed on AWS. BuzzFeed, for instance, is a great example. They're using RDS and Elasticache. Vanguard, who many people probably know pretty intimately, are using DynamoDB and RDS. And again, we see this pattern of building microservices and using different databases for each of those microservices. ZocDocs, again, went from monolith to a more distributed approach using DynamoDB and Elasticache. London Stock Exchange is using a multitude of databases: Elasticache, RDS, Redshift, and Elasticsearch. So I really encourage you going through and looking at some of these different data architectures. You can see how customers are thinking about and talking about building modern applications. So for some additional resources as well, Andy Jassy's keynote at reInvent, specifically the databases section, was a really good description of the databases at AWS. Werner Vogel's blog, A One-Size-Fits-All Database Doesn't Fit Anyone, that was just written a couple weeks ago, is a really good resource. And of course, AWS databases pages to learn more about any specific service. If you want a little bit deeper talk than the one that we had today, there's 2 good 300-level talks. One was at reInvent last year with Tony Petrosian and Ian Myers. Both of them are very great. It's a really good talk about talking about which database to use when. On a similar topic, Rick Houlihan did a little bit different but very useful talk at the SF Summit in San Francisco last year, talking about applying purpose-built strategies, and that was really well received. So I highly encourage you to look at either one of those resources or both. So again, as a quick recap of what we talked about today, we talked about what purpose-built means, and to think about working backwards from your use case to pick the right tool for the job. We went through 6 of the common data models and use cases that we see developers using those for today. We did a quick demo of how multiple purpose-built databases can be used within a single application. We just finished with a few customer examples and some additional resources to learn more. So again, I thank you for your time and appreciate you joining us today. Thank you.